This lecture covers Newton's laws. In this lecture, we're going to be looking at parts of Chapter 5. So first of all, a quick recap of the most important ideas covered in the last lecture. So we saw that when an object undergoes uniform circular motion, the acceleration is directed towards the center of the circle, and it's given by the expression A is equal to omega squared r, where omega is the angular velocity, which is the change in angle divided by time, which is equal to v squared on r, where v squared is the speed. We saw that free body diagrams are a useful way to represent forces, and we met the first of Newton's laws, Newton's first law, that tells us that an object at rest remains at rest, and an object in a state of constant motion remains in constant motion unless acted upon by an unbalanced force. So let's look at Newton's second law. Newton's second law tells us that the net force on the body is equal to the product of the body's mass and its acceleration. So the net force, which is the sum of all the forces acting on the body, is equal to the mass times the acceleration. Now there's lots of questions you can do to practice using this. Homework set 2, questions 1, 2, 3 and 4 for 1121, and 1, 2, 3, 4, 7 and 8 for 1131. Now Newton's third law tells us that for every action there is an opposite and equal reaction. Or we could state it another way. We could say when two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. Okay, so here's an example of a problem where we'll be using Newton's second law. So in this example, we're asked to draw a free body diagram for this system. So with mass 1 here, it's got the weight force m1g pulling it down, and it's got a tension force in the string pulling it up. M2 similarly has a weight force pulling it down and a tension force pulling it up. Now in part 2, we're asked to use the free body diagram to write separate expressions for M1A and M2A. So let's assume that because M2 looks bigger, this is accelerating this way. So we can write for mass 1 here, M1A, the net force on M1 is equal to T, which is pulling it up, minus M1G, which is pulling it down. And for mass 2, which is accelerating downwards, we've got the M2G pulling it down, and then the tension force is pulling it up. So that's how we do part 2. Now in part 3, it says solve these simultaneously to come up with an expression for A. So let's call this one 1 and this one 2. Let's do 1 plus 2. And so we've got M1A plus M2A equals, now you can see we've got a T here and a minus T. So these two are going to cancel each other out when we add these two equations together. And we're left with M2G, which is positive, minus M1G. So we can write A times M1 plus M2 is equal to G outside of M2 minus M1. And so we've got A is equal to G M2 minus M1 over M1 plus M2. We can just check this makes sense in terms of units. The units for the masses are cancelling out, and we're left with the units for G, which is an acceleration due to gravity. If these masses had the same mass, we'd expect it not to move, and we do indeed get 0. So it seems to make sense. Okay, now problems like this are sometimes referred to as Atwood machines. So we've got another example here. A speedy elevator accelerates upwards at 1 meter per second. Okay, so let's draw our man standing in our accelerator. Now it's accelerating upwards with a speed ma. And it says if a person with a mass of 80 kilograms stands on scales in the elevator, so let's put some scales underneath him, what would the scales read? Okay, so like always, we'll draw a free body diagram. So acting on the scales, we've got the weight of the man going down, which is mg, and then the scales are applying the normal reaction force on the man, N, and the resultant is that the scales in the man accelerate upwards with a force ma. So we can write ma is equal to n minus mg. And what we're trying to find is the reading on the scales, which is the normal force. So we've got the normal force is equal to ma plus mg. So we can evaluate this. This is ma plus g, which is equal to 80 times, he's accelerating upwards at 1 meter per second, and this is plus 9.8. So this is equal to 80 times 10.8, which is equal to 864 newtons. Now, typically, you don't read off the scale in newtons. Typically, it will convert this into a reading in kilograms. So to convert it to a reading in kilograms, we need to divide by G, 9.8. So 864 over 9.8 is equal to 88 kilograms. So he's heavier on the scales when he's accelerating upwards. It now says as the elevator decelerates at 1.2 meters per second, we're still traveling upwards. What does the scale read? Okay, so let's draw what's going on in blue now. So now it's decelerating. So if it's decelerating, the acceleration is in the downwards direction. And we've still got the man's weight that hasn't changed. It's the same mg. But now we're going to have a little less normal force acting upwards. So let's write down the equations for what's going on here. Here we've got ma, which is downwards, is equal to mg, which is downwards, minus n. And we want to find our normal force because that's what our scales read. So we have n is equal to mg minus ma, which is mg minus a. And now we can substitute in. This is 80 times 9.8 minus 1, which is equal to 80 times 8.8, which when we solve it on the calculator, we get 688 newtons. But then we want to convert it to a reading on a scale. So 688 divided by 9.8 gives us 70 kilograms. And both these answers have been given to two significant figures because we were given two significant figures in the question. So here we're asked to predict what the balance will read. Both these hanging masses on either side are 450 grams and the scale is here. So it reads off a mass in grams. So have a quick think about what you think it's going to read. Okay, well in fact it reads 450 grams. So a good way to understand this is to imagine that we had one of these masses connected to the wall. So we have a wall there. Here's our balance, and then we have the hanging mass here, which is 450 grams. In this case, you'd clearly expect that the tension caused by the weight force from this 450 grams would exert a 450, well, the equivalent of a 450 gram force on this Newton spring balance, and that it would read 450 grams. But what happens if we have another mass pulling it back this way instead of a wall? Well, in fact, it's the same. Because of Newton's third law, this string pulls on the wall this way with the same force that the wall pulls on the string in the opposite direction. And you can see that that's clearly going to happen here. We've got this tension from this hanging mass pulling this way, while this hanging mass pulls this bit of string this way. So this situation, when we look at the forces, is actually really very, very similar to this situation over here. So that's a good way to understand why it reads 450 grams rather than you possibly thought it was going to read 900 grams. So here's a puzzle to think about. As we all know, a horse can pull a cart along a road. However, if for every action there's an opposite and equal reaction, then the cart must pull the horse back with the same force that the horse pulls the cart forwards. So how can the horse and cart move forwards? so I've tried to draw a horse and cart. I'm sorry, I'm really bad at drawing. Let's now, on our diagram of the horse and cart, draw all the forces that are acting. Okay, so like we said, the horse is applying a force to the cart. So we can draw that here. This is the force of the horse on the cart. Now, Newton's third law tells us that, well, the cart applies an equal and opposite force on the horse. So these two have the same length, and we've got the force of the cart on the horse. Okay, but these are not the only forces acting in this system. If you think about it, when you walk forwards, how are you moving forwards? You're moving forwards because your feet are pushing back with friction on the surface of the earth. So the same thing happens with the horse here. The force of the ground on the horse is forwards, and at the same time the horse applies an equal and opposite force of the horse on the ground. So when you move forwards, because you're walking, you're pushing backwards on the earth. Now let's think about the cart. It's a little bit different because it's being pulled forwards. So it's got a force opposing that motion, the frictional force. So this is the force of the ground on the cart. And then because the ground's pulling the cart backwards due to friction, the cart is also pulling the ground forwards. So G here stands for ground. And the same here, we've got a red G here. This is the ground. Okay, so we've got three sets of force pairs here. Okay, in reality, I probably should have drawn this red one at every single foot. The green one would be at every single wheel. But you get the idea. We've got a whole lot of force pairs here. So how come the horse moves forwards? Well, the horse and cart are joined together. So they're effectively one body. So let's draw a free body diagram for our horse plus our cart combined together. Now, when we are drawing free body diagrams, we do not draw internal forces. So these blue ones here, these are internal. This is the force of the horse on the cart and the force of the cart on the horse. But the cart and horse are effectively one body, so we don't draw those here. It's like if you're drawing a free body diagram of yourself, you're wearing clothes, you don't draw the weight of the clothes pushing down on you and the reaction force of your body on the clothes, because that's just not useful information. What we want to know is what external forces are acting on the body. So let's draw our external forces acting in this case. So we've got the ground, which is pushing the horse forwards. So this is the force of the ground on the horse. It was drawn up here. I've just drawn the same force down here. Now we've also got the force of the ground on the cart. The ground's pulling the cart in the opposite direction, so ground on cart. But these green ones are smaller than these red ones because carts are designed to have very little friction. It wouldn't be a very good cart if it was really hard to get it going because there was so much friction. So this green one is shorter than this red one. So this tells us that there's a net force on. And so the net force is equal to the force of the ground on horse minus the force of the ground on cart. And so you can see that's going to be equal to a little force like that. And that force is what's going to cause the whole thing to accelerate. So if we could measure this, or we knew what this force was, then to work out the acceleration, we just need to divide it by the mass of our system, which is the mass of the horse plus the mass of the cart. So that is why the horse and cart move together as one body, which is accelerating despite all these pairs of forces. So as the horse and cart move forwards, there is an equal force on the ground backwards, but because the ground is so heavy, it's the whole mass of the earth, then we don't see an acceleration in this case because it's just so minuscule. Okay, so now we're going to look a little bit more at external and internal forces. So generally when we're considering total forces acting on bodies, we can ignore the internal forces. So imagine that we had this series of 4 masses all joined with pieces of string, and then we pulled it along this way with some force F. And we're told that we can assume that friction is negligible, and we need to sketch external and internal forces acting on the system above. Okay, so let's start with M4. So M4's got M4G going down, and then it's going to have an equal and opposite normal reaction force going up. Now it's got this force F pulling it along, but these other masses are pulling it backwards. So we'll call this F3 because mass 3 is the one next to it. So those are all the forces which are acting on block 4. So in block 3, we've got M3G going down and normal force going up. We've got this F3, which was pulling back on mass 4, pulling this mass forward. So it's got F3 this way, but mass 2 is actually pulling it backwards. So that's F2. So with mass 2, we've got the normal force and the weight force. And we've got this F2 force is pulling it forwards, while mass 1, F1, is pulling it back. We've got the M1G, we've got the normal force, and we've got F1 pulling it forwards. Now we do have tension in each of these strings. This is how the force 1 here gets from this body to this body. So the F1 is going that way. We've got the tensions pulling these bodies along this way. But these are all as force pairs, so the tension is pulling the string both ways. The tension in this string is just this way, and the ones going this way are slightly larger. So now we're asked if the masses are all equivalent and F is equal to 8 newtons, what is the tension in each of the strings? So let's call this one T12, we'll call this one T23, and we'll call this one T34. And we need to find out what these are. Okay, so the mass of the system is equal to 4 times the individual masses because they're all equivalent. And we can work out the acceleration of the system, because if we consider the system as a whole and neglect all these internal forces, then we've got the force F pulling it forwards, the weight forces and normal forces all balance, so this is the only net force acting. So considering net forces, we've got F is equal to the sum of the masses times the acceleration. And so we can see that the acceleration is equal to F divided by M. Now T34 is the force which is responsible for pulling mass 1, mass 2 and mass 3 forwards. So this is the net force on mass 1, 2 and 3. So we can say that's equal to M plus M plus M times A, and it's this same A here. And so we can write this is equal to F over capital M, which is 4 times little m, times this thing, which is 3m. So we can write this as equal to 3F on 4, and we know what F is, it's 8. So this is 3 times 8 on 4, which is equal to 6 newtons. Now T of 2 on 3, this is the force which is responsible for pulling forwards mass 1 and mass 2. So this is going to be M plus M A. And we can do a similar thing here. We know that the acceleration is F over capital M, which is 4m. So we've got 2m times A, which is F over 4m, is equal to F over 2, which is equal to 4 newtons. And finally, T12, that's only responsible for pulling forwards this final mass. So this is equal to MA, which is equal to M times F over 4m, which is equal to F over 4, which is equal to 2 newtons. So now we've managed to calculate the tension in each of those individual strings. So another example problem, we're told to assume that friction is negligible and the tension in this string is T. So if we're drawing the tension, it's pulling this one up and it's pulling this one up, T, T. And we're asked to write an expression for the acceleration of m1. Okay, so for m1, we just need to consider all the forces acting on it. We've got m1g pulling it down, which we can split into the component parallel to the plane, which is equal to m1g sine theta, and the component perpendicular to the plane, which is m1g cos theta. But when we're considering the acceleration, it's going to be along the plane. So we can just consider the forces which are acting along the plane. So we can say, well, m1a, let's assume it's accelerating up the plane. Then we've got the tension force is pulling it up the plane, and we've got m1g sine theta, the weight force, pulling it down the plane. So that's the answer to 1. Now in part 2, we're asked to write an expression for the acceleration of m2. So here we've got m2a, which is the acceleration of mass 2, which we'll assume it's moving down, and that is equal to m2g minus the tension. Then part 3, if the masses are at rest, derive an expression relating m1, m2, and theta. Okay, so if the masses are at rest, then we know that this thing is 0, this thing is also 0. So we can write, well, 0 is equal to m2g minus t, which tells us that the tension is equal to m2g. So we've also got, looking at the top one, 0 is equal to t minus m1g sine theta. But we can replace this t with m2g. So this is m2g minus m1g sine theta is equal to 0. So we can now cancel g out because it occurs in both terms. So we've got m2 is equal to m1 sine theta. So this relates m1, m2, and theta when the system is at rest. Okay, so here's a problem which isn't too hard. A block accelerates down a frictionless inclined plane with an acceleration of 4.9 meters per second. What angle in degrees does the plane make with the horizontal? Okay, so here's our plane. We've got a mass on it, some mass m, we're not told. It's accelerating down the plane, and we want to know what theta is. So let's draw our free body diagram for our mass. It's got mass mg pulling it down and the normal force pulling it up. Now, the acceleration is down the plane, so we can just worry about the components of the forces which are down the plane. So let's split our weight force into components parallel to the plane, down the plane, and perpendicular to the plane. Now we know that's theta, so this one here is m1g sine theta, and this one here is m1g cos theta, which will be equal to our normal force, but that's not important at this point. So we've got that the net force down the slope, well, there's only one contribution to it, and that's given by m1g sine theta. So the m's cancel out, and we've got that the acceleration, which is 4.9, is equal to g, which is 9.8 times sine theta, which tells us that sine theta is equal to 4.9 over 9.8, which is equal to 1/2. So solving this for theta, we can see that theta is equal to 30 degrees. So that solved that problem. So another problem, the velocity of a 3 kilogram particle, so m is equal to 3 kilograms, is given by v is equal to 8ti plus 3t squared j meters per second with t in seconds. At the instant, the net force on the particle has a magnitude 35 newtons, so F is equal to 35.0 newtons. What is the direction relative to the positive direction of the x-axis of the net force and the particle's direction of travel? Okay, so we have the mass and we have the force. So we can work out the magnitude of the acceleration is given by the force divided by the mass. And this is equal to 35 divided by 3, which is equal to 11.67 meters per second. Now we can also work out the acceleration by differentiating the velocity. So we know that the velocity is 8.00 t in the I direction plus 3.00 t squared in the j direction. So the acceleration is equal to dv dt, which is equal to 8.00 I plus, when we differentiate this, we've got 6tj. Now we can work out at what time the acceleration has a magnitude of 11.67, and from that we'll know what the j component of the acceleration is. So if we know the I and the j component, then we're able to work out the direction. So the magnitude of the acceleration squared is equal to 8 squared plus 6 squared t squared, and we know this is equal to 11.67 squared. This 11.67 comes from up here, and this comes from adding these. So we've got 8 in the I direction, and then we've got 6 t in the j direction. So when we're adding them, we add them with Pythagoras' theorem, which is why we get these squareds here. So solving this, we've got 36t squared is equal to 11.67 squared minus 8 squared, and we can solve that for t, and we get t is equal to 1.415 seconds. Okay, so now we have t, and we can substitute it back into here. So now we've got a is equal to 8.00 I plus 6.00 times 1.415 j, which is equal to 8 I plus 8.4918 j. So now we can work out that angle. We've got 8 in the I direction and 8.4918 in the j direction. So what we want is this angle in here. So we can use, well, tan theta is equal to 8.4918 divided by 8. And so this tells us theta is equal to 46.7 degrees. So that's the direction of the net force, because the net force has the same direction as the acceleration. Part B then asks us for the particle's direction of travel. So that's the direction of the velocity. So we can write the velocity, and we've worked out the time now. So we're substituting the time into this velocity equation. So it's 8 times 1.415 I plus 3 times 1.415 squared. Solving this, and this is in the j direction, sorry I left that off. Solving this, we've got 11.32 I plus 6.006 j, and so we've got 11.32, 6.006, and we want this angle in here. So calculating this angle, we've got tan theta is equal to 6.006 over 11.32, and so theta is equal to 27.9 degrees. So there we've measured the angles relative to the positive direction of the x-axis for these two things. Okay, so in this question we've got a 10-kilogram monkey who is climbing up a massless rope that runs over a frictionless tree limb and back down to a 15-kilogram package on the ground. And we want to know what is the magnitude of the least acceleration the monkey must have if it is to lift the package off the ground. Okay, so as the monkey pulls up on the rope pulls down on the monkey. So we've got a Newton force pair in that case. And so we can consider the forces acting on the monkey. So the rope is pulling the monkey up. Let's call that some force F, which is what the rope pulls the monkey up with. And then we've also got the weight force of the monkey pulling it down. So we know that the mass of the monkey times the acceleration comes about as a result of these two. So if the monkey is accelerating up, then we've got F the force of the rope on the monkey pulling it up, and we've got the weight of the monkey pulling it down like this. So we can write this equation. Now let's consider the parcel here. The parcel has got a weight force mg downwards, where that's the mass of the parcel. It's also got a normal force from the ground upwards, and it has a tension force from the rope pulling it upwards. Now the parcel will lift off. When the normal force is equal to 0. So let's write down the equation for the parcel. The mass of the parcel times the acceleration, which is 0, because it'll just lift off when it's got a net force of 0, is equal to the tension force minus the mass of the parcel times g. Now this tension force is the same as the force that the rope applies on the monkey, because the force from the rope has to be the tension. That's what tension is. So we can say, well, this is the same as F. So we can write this as F is equal to the mass of the parcel times G. Now what we're trying to do is calculate the acceleration of the monkey. So we can replace the force in this equation with this expression here. So we've got the mass of the monkey times the acceleration is equal to the mass of the package times g minus the mass of the monkey times g. So we can say, well, the acceleration is the mass of the parcel minus the mass of the monkey times g over the mass of the monkey. So this is equal to 15 minus 10 times 9.8 divided by 10. And solving this, we get 4.9 meters per second per second. And we could see there that the units were right, because we've got the mass on the top and mass on the bottom, so those units cancel out. And g, that's the same units as this acceleration here, so that's good. Okay, part B now asks us, if after the package has been lifted, the monkey stops its climb and holds onto the rope, what are the magnitude and direction of the monkey's acceleration? Okay, so this then becomes an Atwood type question, where we've got the monkey here and we've got the package here. So we've got the mass of the package times g acting downwards and the tension acting upwards, and here we've got the mass of the monkey times g and the tension. So as the package is heavier, it's going to accelerate this way. So we can say that the mass of the monkey times the acceleration is equal to the tension minus the mass of the monkey times g, and that the mass of the package times the acceleration is equal to the mass of the package times g, which is pulling it down, minus the tension, which is pulling it up. Then we're going to sum these two equations together, so that gives us the mass of the monkey plus the mass of the package times the acceleration. When we sum these together, the tensions cancel out, and we have the mass of the package times g minus the mass of the monkey times g, and so the acceleration is equal to mp minus mm times g over mm plus mp, and so this is equal to 15 minus 10 times 9.8 over 15 plus 10. And so solving this on the calculator, we end up with this is equal to 2.0 meters per second per second. And we're asked for the direction of the monkey's acceleration, that's upwards. And then part D, we're asked for the tension in the rope. So now we can go back to this equation here, and we have the mass of the, we can rearrange it to give the tension is equal to the mass of the monkey times A plus the mass of the monkey times G, and so this is equal to 10 times 2 plus 9.8, which is equal to 120 newtons, and that's to 2 sig fig.